My name is Bharat Seram and this is the independent set problem. So the maximum independent set problem in a graph theory is the task of finding the largest independent set in a graph, where an independent set is a set of vertices such that no two vertices are adjacent. There is currently no known efficient algorithm to find maximum independent sets. The Now let's look at a problem regarding the maximum independent set. So we are given a graph G and we have to find the maximum size subsets of G's vertices such that they have no edges between them. To go ahead with this problem, let's take this approach. Let's choose a vertex V such that NV is triangle free for each pair of non-adjacent vertices U, W in NV. Now we'll construct a new vertex UW that is adjacent to all neighbors of U, also or all neighbors of W or all other new vertices. Now you delete V and NV. So some of the key ideas regarding going ahead to solve this problem is, the subproblems need not be induced subgraphs. Also, we reduce general case to sparse case. Um, so it is important that we note that the subproblems need not be induced subgraphs. So the advantage of this approach is we eliminate degree 2 vertices for free. So this is even better than degree 1 vertices. So in this approach, we first add 1 to the size of the MIS. The same idea works for other special subgraphs as well. Example, a degree 3 vertex with two adjacent neighbors. So we add 1 to the size of the MIS over here, as we can see in the diagram. So now analyzing the following algorithm, we see if it reaches polynomial time. The input, a graph G in which every neighborhood is triangle free. The count is 0 while G is non-empty. We apply a struction to G and count increments, and this loop continues, and the output would in the end give the count. So the again, like I said before, the subproblems need not be induced subgraphs. The disadvantage of this is dynamic programming doesn't work because there are too many different possible subproblems. Let's look at this case where G is 3 regular and triangle free. So we choose any vertex and we recur on GV and GVN. So as by looking at this diagram, we know that the we can get the subproblem of size E9 and we can get the subproblem of size E9. The associated polynomial is 2x power 9 minus 1, whose root is 2 to the power of 0.111. So by using this approach, we can also reduce the general case to sparse case. So low degree graphs already are sparse. In general graphs, degree k vertices yield subproblems of size n minus 1 and n minus k minus 1, which is good for large k. So, but we do even better by reducing the subproblems with degree 2 vertices or other nice graphs. So the possible improvements of this approach is one of our key ideas was to find complexity as a function of E and then to reduce sparse graphs. It might be better to find complexity as a function of alpha E plus beta n and then reduce to sparse graphs. Analyze directly as a function of E and n. Please let me know in the comments. Thank you.